Hello, my name is Taylor Hepler. I would like to introduce you to my teammates, Noah Bolo and Matthew Fontana. Thank you for joining us for today's presentation. Our team is the runner-up for the 2020 SME Digital Manufacturing Challenge. The theme for this year's challenge was Digital Manufacturing for Sustainable Communities. Our team, along with the support and guidance of our faculty advisor, Dr. Sanjavan Manoharan, worked to develop a sustainable solution called the fog collector that could potentially provide relief around the world. Next slide, please. Before we discuss our proposed design, we'd like to give a brief background on why we chose this project path. According to the World Health Organization, approximately 785 million people lack a basic drinking water source, with roughly 144 million dependent on surface water alone. A powerful solution that our team explored was fog water. These small water droplets are readily available resources and can be harvested from a variety of geographical locations, including deserts, coastal, and mountainous regions. This project aimed to investigate the design and functionality of a fog collection device that could be easily modified and manufactured to be distributed all over the world. By developing a scalable design that harnesses the benefits of two types of materials, our team successfully created a device that could aid in bringing clean water to millions. Next slide, please.
Previously alluded to, the main function of this design is to collect fog water. In some areas, fog collectors can collect approximately 1.75 gallons of water per square meter of collector per day. The goal of this design is to have air rush through the holes in the panel, and the particles of water found naturally in the air accumulate in the dimples of the panel and cascade down the panel. This design was designed to optimize the ratio of panel surface area to airflow. Given the pattern-driven design of our collector, the overall dimensions can easily be changed based on application. DFD and FSI verified that the design will withstand moderate gale speed winds with negligible deflection. Portions of the collector will be made of hydrophilic PMMA to facilitate water collection, and the majority of the collector will be made of hydrophobic ABS to enable large droplets to cascade easily down the panel. Fused deposition modeling, FDM, was selected as the additive manufacturing process to produce the fog collector. FDM is capable of manufacturing models with complex geometries that are made of multiple materials. Next slide, please.
Now that we've taken a look at the fog collector and how it's designed, let's take a look at some of the long-term impacts. First off, it provides a low-cost solution to those in need of a clean water source. At a one-time cost of only $12.61 per unit, this is a much lower cost alternative to methods such as desalination or reverse osmosis. This is made possible with the implementation of FDM, so this is a much lower cost as opposed to something such as injection molding, which this device could be made using injection molding. However, the cost barrier, especially the upfront costs of injection molding, make it so expensive. The FDM is also very portable. The FDM 3D printers are also very portable, so this makes it a very viable solution to send out to communities, and they are then self-sufficient, generating their own fog collectors. In addition to cost benefits, there are also some benefits that come with its widespread versatility. The need for clean water can be found in communities all over the world. However, the cause for the need can vary. It can be due to the general vicinity of only salt water. It can be due to the pollution of the primary water source, or it can even be just a general lack thereof. This device could provide a solution to all of these by harnessing the humidity found in the air and converting it to a use more suitable for human consumption. And not only is it versatile in terms of where it can be used, it's also versatile in terms of how it can be used. We designed it to be installed with materials that can be found anywhere, such as screws, zip ties, or even strings. And since it's a square, you can install it in a grid and expand as your needs expand. The fact that it's low cost, portable, easy to manufacture, versatile in terms of where you could use it, and versatile in terms of how you could use it, make it a great solution to send out in natural disaster scenarios. Next slide, please. Lastly, in terms of impacts comes the impacts that excite me the most, and that is the social and environmental impacts. First, this could result in improved health and safety for a number of reasons. Depending on your location, you may have to travel miles and spend hours upon hours each and every day gathering water. This could reduce the physical effort needed to go get that water, and also save time, which then could be spent getting a better education or contributing to your society in some other way. Having this fresh, clean water source could also help decrease in waterborne illnesses, and it has also been found that having a clean water source can decrease non-waterborne illnesses. This was designed to be produced primarily with ABS plastic, and ABS plastic is recyclable. This means that there will be less plastic waste introduced to our earth and oceans. And lastly, FDM additive manufacturing has been found to use up to 50% less energy as opposed to traditional manufacturing methods. So this will result in less pollution from generating that energy. Next slide, please. Together, these factors produce a product that could not only help the people, but also the planet.
Our team found the SME Challenge to be an important endeavor that helped give insights into real-world design challenges. Thank you again for joining our team today.